Okay, well, good morning, everyone, and welcome. It's great to see everybody again. It's my great pleasure to have the opportunity this morning to introduce Evelyn Sander. Evelyn did her undergraduate study at Northwestern University and went on to do her PhD at the University of Minnesota, where she worked with Richard McGehee. She did a postdoc at Georgia Tech and then moved on to George Mason, where she got a permanent position and where she remains, where she is today. In addition to her many honors and awards and grants and students, she's also currently the editor-in-chief of the SIAM Journal on Applied Dynamical Systems. Her research focuses currently on computer-assisted proofs, computational methods for quasi-periodic sets, invariant tori, invariant circles. And she's also doing very interesting work on visualization of mathematical structures using 3D printing. So we're very happy to have Evelyn here speaking today.
Thank you so much for the nice introduction. So this work that I'm going to talk about today is all joint work with Tom Wanner. And just a minute. Okay, so what I want to talk about is a series of different ideas that all come together in the framework of continuation methods. And I just wanted to do a little comparison of numerical continuation, which is a fairly old topic. The idea is you have some bifurcation diagram. This picture is designed to be any bifurcation diagram depending on a parameter. Not any specific one. And the idea of numerical approximation is that you find, using fairly sophisticated techniques, a series of points that give you an indication of what the bifurcation diagram looks like. And in addition, in many cases, you find places of bifurcation along that curve. And the sort of framework of what I've been doing with Tom Wanner for a number of years is to try to develop rigorous continuation methods that give more than just a set of points that indicate the curve, but a set of boxes which are guaranteeing that you have a unique curve inside of the boxes and possible bifurcation points rigorously verified that they are going to lie inside the box. And additionally, some sort of level of accuracy of information about where the curve lies within these boxes. So I wanted to just give a brief summary of some of the ways in which we've applied this, and then I'm going to expand on each of these ideas. So what I'm showing in this introductory time is some of the applications, but then I will be talking in more detail about the theory that went into the rigorous verification of these theoretical statements. So the picture you see here is a 13-dimensional age-structured map for red coral population, and we are able to validate the bifurcation branch that the bifurcation curves that you see, as well as giving a rigorous validation of each of the bifurcation points. And the right-hand side shows that at the Neimark-Sacker bifurcation, you get some invariant curves, although those haven't been validated. In the context of ordinary differential equations, we have looked at a mapping in high dimensions for a discrete model for Allen-Cahn equations. So in this case, the picture I'm showing is for 10 dimensions, but we can also do a 100-dimensional system. And this is just showing that this is a series of saddle node bifurcations where we're verifying the both the bifurcation and the branch. in the context of partial differential equations, we've considered the one-dimensional Ohta-Kawasaki model, and the picture on the left is a numerical picture of the bifurcation diagram at a certain parameter value. So there are two parameters, and at a certain parameter value, we end up seeing this type of picture with a whole bunch of saddle node and pitchfork bifurcations. And then with Jean-Philippe Lessard, we gave a rigorous validation of two parameter continuation of these bifurcation points. And then finally, this is the latest work is using so this is also the Ohta-Kawasaki model, but a slightly different type of approach. The idea here is to use the details of Sobolev embeddings in order to develop a sort of a more natural framework for rigorous validation of 1, 2, and 3-dimensional solutions. So this is sort of a overview of what I'm going to talk about. And I just want to sort of mention some of the related work for understanding the continuation. So numerical continuation starts with Keller and Dodal, and who developed Otto. And there's a large number of people who have worked since then on the development of numerical continuation and refinement. And I am afraid I haven't listed all their names. In terms of our approach, so let me just say that there are many approaches that have many of the same pieces to them, but our approach to making these kinds of theorems for validation is based on a Newton-Kantorovich method that relates most closely to the work of Plum, and Chiarchia and Yamamoto, Areola, and Koch also have done some work in this general framework. And I know that I don't see how many people are here, but I know that like probably at least half of you have also been working in this general framework. And so I apologize for having a fairly sparse list of names. I just wanted to get down sort of the primary people who are definitely most closely related to the approach that I'm going to be talking about right now. And so I wanted to mention the design principles behind this numerical validation, rigorous validation method that I'm going to talk about. So our goals were to have something that was flexible and adaptable, and point-wise estimates at the branch would give full branch validation. So our approach is, remember, is going to be to find a series of boxes, but that cover the entire branch, and that we can say something about the branch being unique inside those boxes, but that is done with a series of point-wise estimates. And then the modular setup, I guess I would say the modular setup goes with the flexibility because you can, for instance, quickly change nonlinearities, quickly change other types of pieces without having to do a whole lot of extra work. And in the course of this talk, I want to talk about both regular and bifurcation points. The idea of the Sobolev embedding is that this should be computationally feasible in more than one dimension. And then finally, by looking at this setting, we're able to be considering weakly differentiable functions rather than having a sort of a smoother assumption on the set of solutions. And so, like I said, this is going to be Sobolev embeddings, and the primary key for the one technical piece that's sort of the hardest to do is a Neumann series estimate. Okay, so starting sort of at the beginning of the underlying theorem, that is, this is a constructive implicit function theorem. And like I said, this is based on work of Plume. And we're assuming we start with a parameter space P and a Banach space X, and G is going to be mapping from P cross X into another Banach space Y. And we're looking for zeros of G as a function of the parameter. And so this theorem says that as long as you have, so the things that are in parentheses in blue are sort of what you would have if you were talking about the traditional implicit function theorem. The problem with the implicit function theorem, as it is usually stated in a course textbook, is that it says there exists a small neighborhood in which you can guarantee certain things, but we want to have specific estimates on numerical bounds. And so this is the role of this theorem, is to extend. So the idea of assumption one is that we know some specific bound on, for some, we have an approximate zero, and that zero has norm less than rho. And then the second assumption is that we have a bound on the inverse of the derivative. Usually in the traditional implicit function theorem, you just know that the inverse exists. And then in order to be able to look at the parameter values, we're going to have two extra conditions in terms of Lipschitz conditions. And this is what allows us to be able to say something about a box by using pointwise estimates. And so these bounds are basically just traditional Lipschitz type of bounds, although in the second one, we're a little bit more lax than you would be in a traditional Lipschitz condition. And then the conclusions of the theorem is that there exists a box in both parameter and, so as it's a box of size d alpha by dx in parameter cross phase space, so that inside of that box, there's a unique smooth curve of solutions. And this is a picture to try and show that, first of all, let me just say that the details of the theorem that I haven't written down here are that, in fact, there's more than just a box. If you have the blue point here is my approximate solution, and the red is the guaranteed actual solution curve. And what the theorem actually says is that you have a region in parameter cross phase space in which you can guarantee uniqueness. And this region is bounded by a line that is in delta alpha and delta x, which depends on L1 and L2 from the Lipschitz condition. And then there's also a smaller region in which you can guarantee the accuracy. So you expect that as you go further from the point that you've actually written your approximation in parameter, you're going to have a smaller uniqueness region and a larger accuracy region, meaning worse in both cases, right? Because you want small accuracy and large uniqueness. And so the guarantee of the theorem also says that there's a quadratic form in L3 and L4 for the accuracy region. And so this picture is designed to show, I mean, obviously this is in the norm. So in one dimension, it would look like this, but in higher dimensions, this is a schematic. But this is showing that the uniqueness and the accuracy region are actually not boxes at all, but rather, shapes that are bounded below by a quadratic curve and above by sort of this diamond shape. And the box that I'm talking about is, for convenience, this rectangular box, which sort of lops off the uniqueness region, although we wouldn't have to. and says that we're guaranteed, as long as we stay within this box, we're going to have uniqueness and accuracy. And the point at which the box stops occurring is where the uniqueness and the accuracy regions match up. So we've extended this for practical continuation to a slanted box. When we extend it to a slanted box, what happens is you have to worry about, so the slanted box, the design is so that the slant of the box is given by the derivative of the curve at that point. And so it's more natural to be doing this because this is a more accurate approximation of your curve. And so the point here is that if you do this, if your box slants too far, you're going to end up not staying in the original uniqueness and accuracy boxes you had before. And so, in fact, this is why the region of existence might be reduced because of this slant of the box. So the idea of this practical continuation is, first of all, that we have these series of boxes, which I've now drawn schematically. The the dot is where we make our estimates, and the box is the box that's guaranteed by those estimates. And since we're only going in one direction, I haven't drawn both sides of the box. The first point, let's say this black point here, can you see when I point? Is that with my cursor?
Yeah.
Okay.
Yeah, we can see.
So this point is where I do my initial box, and then I get a box in both directions, and then at the end of the box, let's say, I have an approximation, and I make another box, and I've only drawn half of that box because I already know the existence and uniqueness inside this first box. So this next box, I'm only drawing half of it because that's the part that I don't have before. Now, when I do these successive estimates of boxes, in order to guarantee that I don't have some situation like this one drawn here where there's actually two boxes where I can guarantee uniqueness and accuracy, but in fact, the object that I'm guaranteeing uniqueness and accuracy of is two different branches. In order to avoid that, I have to make some sort of a condition that links up my boxes so that I can guarantee that I have the same branch in both boxes. And rather than give the condition now, I'm going to give it in a little bit. I'm going to give it later when I develop my my refined version of this theorem. And so anyway, the point is, by doing this successive boxes that are linked together, we can actually get validation for an entire branch at in this so basically find the box, show that the boxes link, and do this successively, we can get these entire branches. And we also came up with a separate way of writing the coordinates in such a way that we could validate saddle node bifurcations. And so I want to describe how we use this method in the case of the discrete Allen-Cahn model, so the Allen-Cahn model for solidification of phases is a differential equation, but the problem with this differential equation is that it doesn't explain a physical occurrence, which is the pinning of fronts. And so the spatially discrete Allen-Cahn equation was designed with the idea that by looking at a discrete version, it would be possible to explain the pinning of fronts. So it turns out that that as long as you're starting at that we can actually say something about the stable solutions to this, as long as you're far enough out in the parameter. I want to just point out this parameter lambda, as long as you're far enough out in the parameter lambda, and we're using this particular nonlinearity, we can guarantee the existence of stable branches. And this is a theorem that's already known. These are called mosaic equilibrium solutions. And so what we were interested in is understanding how long do these solutions persist. So if these solutions persist for small lambda, which corresponds, I didn't say, but to this parameter here is 1 over the interaction length. And so if it persists for small lambda, that corresponds to a large value of interaction. And so what we did was we did numerical continuation of each of these solutions. It turns out that at dimension 10, or at dimension n, there are 2 to the n solutions, 2 to the n of these mosaic solutions. And so we weren't able to validate all 1,022, but we were able to validate 960 of them. And in addition, we were able to validate the saddle node bifurcation point for each of them. And using that, what we were able to do is you can talk about the grain size, which means the length of the length of the part of this mosaic solution, which is at one particular value. So this is going to be a small grain size because you see it just bounces up and down, whereas this is going to be a larger grain size because it stays at a value for a while. And so we were interested in understanding how this worked, because there'd been some theory that said that that the grain size and the robustness of the solution, meaning for which lambda the bifurcation occurred, would be related. And so we were able to actually validate that using this using these bifurcation diagrams. So one of the things I'd like to indicate with this example is that from the traditional numeric, so if you weren't interested in validated numerics, which doesn't apply to very many of you, but probably you have to talk to people for whom that applies, right? When you talk to a computer scientist or even just a numerical analyst, what do you say to justify why you're bothering with this? And so this is what Otto thinks it sees when looking at some of these bifurcation. We had 960 to work with. Some of them are a little bit weird. So what validation proves is this picture over here, which seems very surprising because this doesn't even look like it's smooth, which shouldn't happen. And what actually multiple validations show is, in fact, this is a more accurate portrayal of the situation, that in fact, there's 2 that come up against each other, and that looks very strange because that's not really a pitchfork, but so if we zoom in, this is what we see, that in fact, what's going on is smooth. It's just that there are 2 solutions that come near each other, and it would be very easy to jump from one to the other, because if you're trying to predict what happens to this curve, you would think that this curve would be the continuation of it. And so by using validation, we were able to actually get more information out. So this is a nice motivating example in the sense that the validation allowed us to do better numerics. Okay, so even if you thought of the validation as just a sophisticated way of double checking your numerics, we got something out of this. All right, so now what I want to do is say that this is a flexible method because we were able to easily swap in a new nonlinearity and go from dimension 10 to a dimension 100 without a whole lot of extra work, because of the modular way that this method was designed. It didn't involve a whole lot of extra coding in order to be able to validate in this new setting. So the problem, if you are familiar with numerical continuation methods, you've already seen the problem with what I've just described is that it was a natural continuation method, in the sense that we were only doing a progressive, we would look for a point in our method by fixing the parameter. And that's not actually the state of the art of numerical continuation. So we developed a new method which is the validated pseudo arc length continuation method for this. And so the idea here is, so, you know, from the schematic, it's not very important, but it is sort of critical that now these boxes we're validating have slanted sides instead of straight sides. And the idea here is to think about that we're still able to validate this curve, and this is the uniqueness and the accuracy regions in roughly the same colors as before, and the verification of the branch based on a single point. But the idea is that the new point that we find is is found by looking orthogonal to the direction in which we are slanting our box. Okay, so this actually allows us to, for example, automatically find branches that go around corners, rather than in the previous picture, we had to separately validate near a saddle node bifurcation. And so this is much more flexible because of this. And we basically, the idea is that we can, that sort of the main thing we have to add to this is that we have to assume that this condition is small. So we're going still, everything we're doing is from the constructive implicit function theorem, but the idea is that instead that basically we're using the constructive implicit function theorem in an extended system in order to be able to more quickly and efficiently use the numerical part of approximating the solution. And the thing that I said before, I wasn't going to tell you about the linking condition for the boxes until now. So let me now tell you in the pseudo arc length continuation what the linking condition is for the box. The idea is that we have some point that we validated. We have some direction that we are validating in terms of this box. And then we have a, then we choose a point somewhere in the box and validate or approximate with a new green dot what our next guess for a solution is. And in order to make sure that these boxes are actually validating the same branch, what we need to guarantee is that the K plus first box, if you just look at the initial points, right? So I'm not talking about the entire box, but the initial points. The initial accuracy interval of the K plus first box must be inside the uniqueness of the Kth box. And so this is a condition that can be validated, can be fairly quickly checked as part of a iterative process. And what we applied this to was a 13-dimensional age-structured coral population model, and some somewhat unnecessary but beautiful pictures of red coral. The idea is that this model is based on the idea of a colony, and an individual polyp is an individual coral animal, but the polyps live in colonies. When the polyps are born, they're able to move around, and then they join a colony. And if they don't join an existing colony, then they're called recruits, where they form their own colony. And some Bramante, Ainelli, and Santagalo went scuba diving off the coast of Italy. They're biologists, and actually counted the number of the number of polyps in a colony depending on the age of the colony. And so we're using this information in order to make a model. It may seem from what I said before that it's a linear model, but the key point is that the density of the polyps is going to affect the number of recruits. And so what we did was we added a fitness parameter. So they had an existing population and an existing assumption. And they had already sort of made this as an indication, but we've added a fitness parameter to sort of see how the populations would change as a parameter of fitness of the coral colonies. And the this is the validated picture. The 0 picture is validated by hand because it's very simple. The rest is not. I want to make a comment here that preconditioning is critical for this to work. If we hadn't preconditioned, we basically wouldn't be able to validate even a fraction of these. We ended up validating like a little tiny bit in the corner and just couldn't go any further. But once we've preconditioned, we're able to validate this whole curve. In addition, we've written down extended systems in order to be able to validate each of the Neymark-Sacker saddle node and transcritical bifurcation points. And then we have to separately check the non-degeneracy conditions. They can also be checked using interval arithmetic, but they cannot be checked just using an extended system. So there's an additional check to make sure you have a bifurcation that fits the traditional theorems. I put a warning, an advertisement in, because if we follow the invariant circles that occur at the Neymark-Sacker bifurcation, we get some interesting behavior. I want to just say that this is not validated, but I think it's a very interesting idea to try to validate in the case of quasi-periodic orbits. I know that we've heard Elena Carrillo talked before about validation of periodic orbits of ordinary differential equations. This is going to be a little bit different because these are quasi-periodic orbits that are not made up of a single solution. And in some cases, these will be periodic orbits that consist of distinct points, but you can't really see, they're very high periods, so you can't really see. So I wanted to just mention that what we did is we asked the question, on each of these curves, as you're moving around, I've labeled the angles from 0 to 1. And I want to know at each point along this curve, how much on average are you moving when you iterate? And so as a function of angle. And what you can notice is that at around a little over 0.6, which notice is very near the extinction point, the amount by which you're moving is very, very small. So what that means is not only do you get very close to extinction as these invariant curves grow, but you also stay there for a very long time. So in fact, as the fitness grows, not just as the fitness decays, you end up with a situation where your coral is dangerously close, the population is dangerously close to extinction and stays there for a very long time. So any perturbation could put it over the edge. And I just wanted to comment about why it is that I do not, pretty much never see anything but what look like quasi-periodic orbits. And that's because, in fact, the lowest, so we can calculate the rotation number of the curve. And when we calculate the rotation number, see that it, for the entire set of these, lies between 0.126 and 0.129. And so we can calculate that the smallest rotation possible in that period is 39, is period 39. So the reason that we don't see a lot of devil's staircase behavior where you see periodic orbits among the quasi-periodic is because of this high period. So I am now going to end my my non-validated part of the talk and move on to looking at Diblock copolymers. And so Diblock copolymers are what are making up upholstery foam, adhesive tape, asphalt additives. And here's some pictures of electron micrographs of the types of microphase separation that you get in these materials. And so you end up with, these are some schematics of the types of behavior you get. And it's based on the fact that you have two different types of polymers, and they are interacting, but they're bonded, but yet they're repelling each other. So you get some interesting behavior in this case. And the model for this behavior is the Ohta-Kawasaki model. And I just want to say, if you're familiar with the Cahn-Hilliard equation, if you remove the red piece of this equation, you end up with the Cahn-Hilliard equation. So sigma equals 0 is Cahn-Hilliard, which is a model for phase separation in binary alloys. If you remove the Laplacian in front of this term, what you end up with is the Allen-Cahn equation. So all of these things are sort of part of a similar class of equations, but I want to talk about this one in particular. We are using a cubic nonlinearity and Neumann boundary conditions. And so this is a list of people who have worked on this Ohta-Kawasaki model before, and in particular, Vandenberg and Williams have also worked on rigorous validation in this model. What I had, so the red on the lambda is because the interaction parameter epsilon going to 0 is inconvenient from the point of view of bifurcation diagrams. So we've rescaled time in such a way that the lambda is going to infinity corresponds to epsilon going to 0. So 1 over epsilon squared is lambda. So here's a bifurcation diagram. These are not validated. These are numerical bifurcation diagrams. This is for lambda equals 0. Well, I should say this is validated. The lambda equals 0 case has been proven because that's the Cahn-Hilliard equation in 1 dimension, which was proven by Novikov and I forget who the second author on that was. But this is for sigma equals 6. And you can see that there's an awful lot of bifurcation points in this case. And so when we saw this, we were interested in what you could say about these bifurcation points. And so with Jean-Philippe Lessard using the radii polynomial validation. So this is, not everything can fit perfectly into my story, but we just developed an extended system for trying to validate these things. And then we're able to validate these 2 parameter continuations of the Ohta-Kawasaki models for saddle node bifurcations and for symmetry breaking pitchfork bifurcations. And so what I wanted to briefly say is, okay, so these 2 saddle node bifurcations are actual, so the blue is the actual solution, and the orange or red, depending on which color you see here, the orange red is the kernel of the linearization at the bifurcation point. And you can see sort of this mini bifurcation diagram with a red dot showing you where you are in this bifurcation diagram from the previous picture. And these are actually at the same point because these are actually symmetric to each other. So these are only represented by one of these 3 curves. There are 2 other saddle node bifurcations that we also have a validation of, and these are these 3 branches shown here. So, you know, one of the things we would like to do, although we, you know, we haven't gone further with this, is that there are some scaling, there appear to be some sort of scaling properties of these saddle node bifurcations that would be nice to be able to say something rigorous about. So in the case of symmetry breaking pitchforks, I just want to make a quick comment. You see 4 solutions and 3 curves. And there's a reason for that. So in order to have a symmetry breaking pitchfork that we can prove, our extended system theory was for Z2 symmetry. And in order to have a symmetry breaking pitchfork that breaks the Z2 symmetry, we need that the the symmetry of the solution at the bifurcation and the symmetry of the kernel, or I should say the represent, you know, the function that spans the kernel have to be different. And you can see that in this picture, and this picture, that is true, that you get the difference in Z2 symmetry. On the other hand, in this picture here, you have odd symmetry in the solution and also odd symmetry in the kernel. And so this is actually outside of the framework of our symmetry breaking pitchfork analysis. And we'd like to go forward, but in terms of being able to understand this as well, this is a problem we're hoping to be able to solve. But anyway, this is the validation of the 2-parameter continuation of these symmetry breaking pitchforks, in which we're able to actually also validate the broken symmetry. Now I want to go on to the Sobolev approach, and Vincent, I apologize for the fact that this didn't take up the majority of the talk, but anyway, here goes the Sobolev approach to.
Well, kindly apologize. Don't worry.
Okay, so the idea here is that we would like to be able to, like I said, extend beyond to looking at weak solutions where we're actually using the natural spaces to consider these things in. So we're going to be looking at rectilinear domains, and so we can write down in closed form that the eigenfunctions for Laplacian are products of cosines, and so I'm going to just define the psi k to be these things, and these are ck is designed so this is a complete orthonormal set, and kappa k is given in this way, and this is going to be this is going to be the eigenvalues of the minus Laplacian. So this is designed to be in dimensions 1, 2, and 3 because I want it to be flexible again, so I can do easily go from dimension to dimension in terms of being able to validate. I also want to mention that when I refer to k, I'm referring to a d-tuple of k values. And so that u of x can be written in terms of a sum over of these psi k's, of alpha k psi k. And one thing to keep in mind here is that I have incorporated the Neumann boundary conditions into my complete orthonormal set. And so when I refer to HL, what I mean by that is the U such that the U written in this form such that the HL norm is less than infinity. And when I refer to HL bar, what I mean is I'm going to assume that alpha 0 is 0. And that means that in addition to incorporating the boundary conditions into my setting, I can also be incorporating my conditions on mu into my, so this is a condition where I'm able to convert the mass into a parameter rather than being part of the equation. And then some norms. So these norms are not, well, this norm here is not necessarily the standard norm, but it is equivalent to the standard norm. And this norm here, I'm using these norms in terms of, these norms are good because these are going to make it easier to work with things because everything is written in terms of eigenvalues of the Laplacian. The thing that, so Wanner in 2018 wrote a paper, so there are these Sobolev embeddings of various spaces inside each other. And what he realized is that it's actually possible if you write it in this setting to not just say that you have an embedding, but actually come up with validated values for the embedding constants. So that's really nice because that means that we actually don't just have embedding, but we have an actual value we can work with. And so this is an extension of what was done in 2018. We've actually come up with not necessarily the best possible, but pretty close to the best possible constants that we were able to get. You couldn't do too much better than this for these embedding constants. Now, what I want to do with this is to come up with a way of writing down validation information for the Ohta-Kawasaki model. So first of all, what is hard and what is easy? What is straightforward is Lipschitz bounds in all three parameters. So I'm going to just quickly remind you, this is the Ohta-Kawasaki model. We're interested in this form of it, where we have, where we're just looking for equilibrium solutions. And so the three parameters in question are the lambda, the sigma, and the mu. And so the easy part is the Lipschitz bounds in all three parameters. And finding a good approximate solution is a numerical problem, which I mean, it's, I don't know if straightforward, but we have some candidates. And then the hard part of this estimate is estimating the derivative inverse. And so I want to use my Sobolev embeddings as well as a Neumann series argument. So just writing down the Neumann series for the theorem, basically what this says is if you have a good approximate inverse, so if you have a linearization L, if you have a good approximate inverse S, by which I mean that I minus SL is less than rho 1, which is less than 1. Okay, so the smaller rho 1 is, the better this theorem is. And if you know the norm of your S to be rho 2, then what the theorem says is that the approximation of that basically you have a bound on the inverse of L. The norm of the inverse of L, if rho 1 is pretty small, is only going to be slightly bigger than rho 2. And so that's what we're going to use. And so let me go ahead and explain. So again, this is the linearization for the Ohta-Kawasaki equation. And the spaces I'm going to be working in are H2 bar and H minus 2 bar, because when you take each of these Laplacians represents two derivatives reduction. So you end up going from X into Y. The projection of the linearization, what I'm using for the projection of the linearization is I'm just going to assume that the maximum of each of the K1 through KD, where again, D is the dimension of the space, is less than or equal to N. So I'm taking only the a partial sum, so a finite sum. And then I'm going to let Ln be the projected linearization. So now we're in finite dimensions. And here's my, so let me just tell you about T inverse. On the space that consists of everything that's, the I minus Pn applied to the space X, on that, which I'm going to refer to as V infinity here. So T inverse on V infinity is going to be defined to be equal to this operator. And so to clarify, I'm just going to remove the hard part and leave the part that I can solve by hand for this operator. And I'm going to have my approximate inverse be equal to the finite dimensional approximation of the inverse on the projection space plus T on the rest of the space. So the interval arithmetic involved comes from estimating the approximate inverse Ln inverse. And once we have that, our theorem is, and this is a bit technical, but Q of X is just lambda times F prime of U of X plus mu. And so just so you know what all these constants are, N, remember, is the projection dimension. And if there's a constant tau less than 1, so that this rather complicated formula that comes from the details of the Sobolev embeddings is less than tau, then what we can guarantee is that the inverse of the infinite dimensional operator is less than or equal to the max of kn and 1 and over 1 minus tau. So you can see the over 1 minus tau sort of indicates where the Neumann series comes into this estimate. So using this, we are able to basically come up with estimates for K, which is this whole piece here. And we're able to get solutions in 1, 2, and 3 dimensions. So I wanted to show you, so when I say that I'm going to basically do that, I have it on, all right, in 1 dimension, here are some solutions. There are 10 of them. And the lambda value is 150, the sigma is 6, and then mu is a variety of values. And this is basically for a typical solution of each type, what type of accuracy do we get? So if we were to choose a larger n, we would get better estimates, but just to give you an idea of what type of estimates we get in each case. And this was basically done in an asystematic way. Basically, I chose n to be something that I wasn't too impatient to wait for it to finish. So like I said, you can do better if you were more patient, for example, but that's not really the point, because I just wanted to give some ideas. So when I say what these values are, remember that I'm assuming that I have I have a point that I've approximated, and I'm interested in knowing the box size in each of 3 directions, because I have estimates on lambda, sigma, and mu. And so in fact, my box is no longer going to just be in 1 direction in parameter space, it can be in 3 directions in parameter space. And you can see right from looking at this that for instance, the mu parameter has way better estimates just because of, or sorry, way worse estimates just because of the nature of how the parameter comes into the problem. But anyway, this gives you an idea of the type of thing you see in 1 dimension. In 2 dimensions, we had 17 total solutions. This is a representative 4 pretty pictures, but to represent the 17. And the n is much smaller here. Well, this one's not so small, but the idea is that n is the calculation goes like the square of n in the 2-dimensional case. And so you end up having to wait longer if you choose n to be a same value. And then finally, in 3 dimensions, here's a solution we validated, and n is 22 because you're looking at the cube of n as the length of time you're waiting. And the dimension of L sub n is going to be very large, and so it's becomes much harder to calculate. So I want to say that this is a story in progress. I feel like first of all that we've developed some theory, but further implementation and optimization is obviously needed. In 3 dimensions, it's not just because there's timing issues. This works, but it doesn't work well in 3 dimensions. And so we need to address these types of things through analytical means, not just through some kind of optimization of our code. And then, Vandenberg and Williams considered reducing dimension via symmetry, and that's something that we could do. But if we wanted to consider non-symmetric equations, then non-symmetric solutions, then we wouldn't want to do that. And so we haven't experimented with choosing symmetric solutions, but that could fit into this framework. And I'll go ahead and stop with this. Here are some references, and thank you.
Thank you very much, Evelyn. I think Jay had to apologize. He had to go quickly to a departmental meeting.
Oh, okay.
Same thing with Vincent, so I'm going to take over the chair. Thank you very much for a beautiful talk. Are there any questions or comments?
Yes, Jean-Philippe. So since I have also a department meeting, as you kindly say, I have a question to Evelyn, because I'm very impressed by the talk. That's one thing, but you were saying, you know what, in the middle of your talk, something about Ohta, and Ohta was not doing the great job that that a bunch of people are saying. So could you explain me what is wrong with Ohta in the example you gave us? I think it's really interesting.
Well, I'm not sure I would say that this is something wrong with Ohta as much as just the design is such that if you have two solutions that are too close together, especially if you have a rather sharp bend, even though it's smooth, it's pretty sharp on the larger scale. What's going to happen is you're over here and you jump in a natural way, because this is what the derivative seems to do. And if you jump, you're going to end up on the next branch over. And since Ohta doesn't include any way of telling whether you've just jumped branches, you just have no information. And what I would say is that you could dial down the jumps in such a way that that doesn't happen for this particular solution, but there's always going to be one that is actually even closer together for which that would happen. It's not possible in a numerical way or at least in the setup of Ohta, it's not possible to avoid the fact that you won't know.
All right, thank you. I think it explained a little bit what is going on, but still, I mean, I still believe that Ohta should be improved with that respect. Anyway, so that's
absolutely. I mean, right. So like this method of validation could be made into a numerical check that could go into an Ohta and whatever Ohta or something like Ohta. I absolutely agree that could be done.
All right, so now I won't bother you anymore. I need to leave. Sorry.
Thank you.
All right. Okay, thank you very much for the question. So are there any other questions or comments?
Yes, I also have a question.
Sure, Michael.
Concerning the setting of your Sobolev spaces. You introduced these spaces for general L, but for which L did you really solve the problem? This fourth order
2
problem.
and -2.
Okay, so I see. So you started from H2 and the range space is H minus.
So this is all, or I should say, yeah. Here are the ones that we were really working with.
So that you wrote it. I'm sorry. Yeah. Yes. So that means that
this idea of being flexible. So I'm hoping that this will not be the only problem that ever has this applied. So I mean, developing it in the HL setting means that you could presumably make it for other L in other settings.
So what I want to say is that for L equals 2, of course, the space does contain the first boundary condition, the Neumann boundary condition for U itself, but the space does not contain the second boundary condition, right? Because the trace is too high. That's this third order derivative d over d nu delta u that's not captured by the traces of H2. But I guess nevertheless it is everything is fine because you're working in H minus 2 in the range space. So that means that the second boundary condition is not contained in the space, but it's just a natural boundary condition of the weak formulation of the problem, so to say.
Yeah. Mm-hmm.
That's okay, because you said that the boundary conditions are contained in your spaces. Of course, that's only true if L is high enough, right? For example, for L equals 1, there is no boundary condition contained.
Right. Yeah. So, right, so, but I mean, maybe this is the wrong way to say it, but the idea that we're writing this in the form of a linear combination of these psi k's is enough to actually contain both of the boundary conditions, because when you know, is assuming that you always stay in this space, then when you differentiate twice, you end up with that condition.
But the problem with this argument is that in the limit, you may lose smoothness and you may lose boundary conditions. And that's what I want to say. So if the limit is in a space HL with too small L, then you lose the boundary conditions in the limit. So for L equals 1, nothing is left. So H1, your H1 is simply the whole space, the usual Sobolev space H1 without any boundary condition. But when you do it for L equals 2, then it's correct, and the du over du survives the limit, and the other boundary condition is just created by the weak formulation.
Yeah, so I suspect that what I should have really said here is this incorporating boundary conditions should have actually gone more like here rather than over here. Because absolutely, you know, this is specific to the number 2.
Yeah, yes, that's what I want to say, yeah.
Yeah.
Yes, thank you.
Thank you.
All right, other questions, comments?
I have actually one more, if I may.
Of course you may.
So in the when you talked about these branch following and the boxes, and you said that the what do you say, the existence region of the case box must be contained in the uniqueness region of the k plus first box, or vice versa.
I think it's vice versa.
Yeah, but what I want to say, it doesn't matter. I think it can also be, you can take it vice versa. I think only, so if one of the existence boxes is contained in the uniqueness box of the other one, then you're fine, aren't you?
That's right.
So you could also in the right picture, in this picture, you could also have the well, so if one of the two is contained in the uniqueness box of the other one, then both solutions must be equal.
Okay. Yes. That makes sense. Yes. Yeah. I mean, I guess it would be harder to check the other way around in terms of, but you're right. Yes, that totally makes sense.
At least there's, first of all, that gives possibly an additional degree of freedom in choices of parameters, and secondly, it's a little bit, it looks nicer formulating it like this, I think, because that shows the symmetry of the argument, because there is no natural direction, strictly speaking.
Right. Yeah. I mean, for example, I mean, I'm thinking of an iterative scheme, right, starting here and then going here, but in fact, there's no reason for that. Like, we could have started on the other direction and gone this way. So yeah, you're right, that would be a cleaner formulation.
Yeah, right. Thank you.